Okay, everyone. Today we're going to cover the chapter 2.4, the work and energy in electrostatics. Okay, so first of all, let's describe how to calculate the work it takes to move a charge. Let's look at the figure 2.39. Let's say now you have a lot of point charges. When you move them from infinity position to closed positions like shown here. So how much work do you need to move them together? So in this figure, it shows you a difficult case because there are several charges, but let's do it from the very simple case, which is just the energy between two charges. Now, let's draw two charges. What's wrong with the pen? Can't draw. So, okay. So now let's see the easiest case, which is Q1 and Q2. Now, if you have two charges and the distance between them is, let's say, R, let's suppose at the beginning they're infinitely far away from each other, and then you move Q2 close to Q1, and then finally they are in the distance of R. Then what is the work? Okay, now let's say at any point along the path, the electrostatic force on Q equals to QE. Okay, let's say at this position, the force F equals to Q2 times E. So when you move it from very far, when Q2 is here, F still equals to Q2 times E. But the E, the electric field here and here, of course, is not different. It's not the same. So E is updating, but Q2 doesn't change from one position to another position. So the force you must exert in opposition to this electric force is negative QE. So let's say the force generated from Q1 to QE is in, let's say, in this direction. This is the force direction. Then if you want to overcome the force and move the Q2 to some positions of QE, then the force you need to do must be in the opposite direction. Then the work you need to do is therefore this force is negative QE, and then you can use negative QE dL, which is a force at a very short displacement. And then you can do a integral, let's say from position A to position B. If this is position A, this is position B, then what you do is you just do a line integral or path integral of f dl. And f equals to negative QE, which is overcoming the electrical force. This is the electrical force, let's say Fe here. And your force should be in the opposite way, so it's negative QE. And then if you do this integral, you will get Q VB subtracted by VA, because here we have been doing this in previous chapters. It equals to the potential of B subtracted by the potential of A. And then the answer is independent of the path you may take from A to B. So let's say from A to B, no matter which path you choose, the answer is the same. It's a VB subtracted by VA. We have been talking about this many times, and we call this is a conservative force. So no matter which path you choose, or this path, it doesn't matter. So the potential difference between A and B is independent from the path. So it's called conservative. Okay. So in words, the potential difference between points A and B is equal to the work per unit charge required to carry a particle from A to B. Because the work equals to Q times the difference of potential at B and A, then the potential at B and A equals to the work over Q. So you get this statement. And in particular, if you want to bring Q from far away and stick it at point R, then the work you must do is, okay, so here we bring it from A to B or from B to A, but if you want to bring it from infinity far away, then what you can do is just substitute substitute, let's say A into infinity far away, infinite position, then it's a VB subtracted by V infinite. Actually, usually we define V infinite to be 0 because we define the potential at the infinity to be the reference. So your work equals to Q V R. R means when the charge A and charge B, or charge 1 and charge Q, they're at a distance of R. So in this case, potential is potential energy per unit charge, because V equals to W over Q. Okay, so that's the calculation of point charges for 2-point charges. Now, how much work would it take to assemble an entire collection of point charges rather than just 2 charges? Now, let's add the charges one by one. If you look at this figure, actually, let's let's move this figure here so that it's more clear. If we move it here, now let's say you have 2 charges. How to calculate the work you need to do when you add the 3rd charge? So what you can do is now, okay, so now you have the 1st charge. It doesn't take any work since there's no field yet to fight against. Now, if you bring the Q2, then you get the equation, which is shown here. W equals to Q times VR. Then if you move Q2 from infinity to the position R2, then you get this equation, W2 equals to 1 over 4 pi epsilon 0 times Q2, and Q1 over R12. R12 means the distance between Q1 and Q2. This is the work you need to do to bring the 2nd charge from infinity to the distance of R12 between Q2 and Q1. Now, if you want to add the 3rd charge, then it requires the work Q3, V12, R3. where V12 is the potential due to the charge 1 and charge 2. And this potential generated by Q1 and Q2 can be calculated by this equation, 1 over 4 pi epsilon 0, then Q1 over R13 plus Q2 over R23. So this is a superposition, the rule of superposition. Superpose Q1 and Q2, you get a superposed electric field of charge 1 and charge 2. Also, you get the potential superposed by Q1 and Q2. So the work to generate, to assemble the third charge from infinity to the position that you need to calculate is shown here. So 1 over 4 pi epsilon times Q3, then Q1 over R13 plus Q2 over R23. Similarly, the extra work to bring Q4 can be written in this format. And the total work necessary to assemble the first 4 charges is shown here. You can see 1 over 4 pi epsilon 0, Q1, Q2 over R12, Q1, Q3 over R13, Q1, Q4 over R14, then Q2, Q3, Q2, Q4, Q3, Q4. So if you want to summarize the entire terms in the parentheses, you can see the general equation, which is take the product of each pair of charges divided by their separation distances and then add it up. Then the work for the total charges is 1 over 4 pi epsilon 0. Then 2 sigmas of Qi Qj over Ri Rj. And be careful that n is from I, the I is from 1 to n. That's the first indices. The second index is j, which j is greater than I, and it's from I plus 1, let's say, to n. And this j is greater than I is to remind you not to count the same pair twice. For example, you can't do it like QI over RII because RII, it's not the work generated needed to generate the set of the charges. It's the self energy by QI. So we don't want to want the indexes to be the same. So a nicer way to accomplish the same equation is still sigma is from I to n, and then j is from 1 to n again, but j doesn't equals to I. In this case, you double counted every pair because, for example, Qij could be Q1, 2, Qji can also be Q1, Q2. So you need to, so each pair has been double counted twice. So you need to divide it by 2, which is 1 over 8 pi. Okay. Now, this is a set of charge. Let's see if you, okay, so if you pull out the factor Qi, because in the previous equation, it's Qi, Qj. So if you want to pull out Qi, then it equals to this equation. The work equals to 1 over 2, the sigma of Qi, then times the sigma of 1 over 4 pi epsilon 0 Qi over Rij. And what's this in the parentheses? if you look at this term in the parentheses, then actually this is VRI. So what you can do is you can write this equation in another form, which is work equals to 1/2 sigma of QI times VRI. And VRI is the potential at point R due to all the other charges. So that's how much work it takes to assemble a configuration of point charges. It's also the same amount of work you need to get back if you disassemble those systems or move all the charges to infinity positions. Okay, so previously we have fully described the energy you need to assemble point charges. In a more comprehensive case, let's see the continuous charge distribution. If it's not point charges, instead, if it's a continuous charge, what do we need to do? Now, let's see, for a volume charge density rho, the equation of 2.42, this equation becomes 1/2 rho v deta, because here it's point charges, so you can use sigma to sum them up. But if it's a continuous distribution charge of the charge, then the sigma could be replaced by the integral. Now you just need to do the integral of the charge density times v times theta, because charge density theta, it's the infinitesimal charge, so charge times v, which is the same as in this equation. And then this corresponding integral for line and surface charge would be lambda v dl and sigma v dA. And there's a good way to rewrite this result, in which rho and v are eliminated in favor of E. First, use Gauss law to express rho in terms of E. So rho equals to epsilon, the gradient of E, and then the work equals to epsilon 0/2, then the integral of del dot E times V dt or deta. So here we just replaced the rho by epsilon 0 times gradient of E. Now, let's use integration by parts equation 1.95 to transform the derivative from E to V. If we want to transform this derivative from E to V, so what we can do is let's use 1.959. Here I showed the equation of 1.59 here. So the integral of f times the gradient of a times theta equals to negative a dot gradient of f theta times a surface integral of fa dA. If you forget this equation, you can go back to 1.59. It's not a difficult equation. It's just a very simple rule, because if you move this term to the left and this term to the right, you figure out it's just a very regular equation. So if you forget it, please go to the chapter 1 to see the derivation of this equation. And then if you use this equation to convert the work calculation here, then this equation becomes the work equals to here. So you make this one term into those two terms, and del V equals to negative E. So here, del V could be replaced by negative E. So here it becomes epsilon over 2, then first, a volume integral of E squared deta times a surface integral of VE dA. Now, once you get this equation, this is the same for the work. You need to assemble a continuous charge distribution. Now, using this equation, you will get some interesting features. So first of all, let's see. If you do a volume integral and surface integral, so now let's see which volume should we use to do the volume integral or surface integral. Of course, it should be the volume which contains your continuous charge distributions, and then the surface which covers this volume. However, you can extend the space or the volume you do the integral, because if the volume is outside the continuous charge distribution, then there is no charge. So the integral at the extended area or volume should be 0. And the same thing, you can extend your surface integral into a bigger surface. So if we can extend it, then why not let's extend it to infinite far away? Then you still get the same answer from here, from this equation, because no matter how big it is, once your integral volume covers your continuous charge distribution, then the answer is the same, because outside the continuous charge distribution, simply the integral is 0. But it brings you a feature, because at large distance from the charge, E goes like 1 over R2, and V goes like 1 over R, while the surface area goes like R squared. Roughly speaking, then the surface integral goes down like 1 over R. So let's see. So if we choose the integral space to be infinity large, then this term becomes a 0, because as we said, V goes like 1 over R squared, E goes 1 over R, but dA goes R squared. So totally, if you calculate this term, it's getting decreased when you increase the distance or space from the continuous charges you want to calculate it. So if you increase the integral into infinity space, then that term simply becomes 0. And then you get only the left term, which is work equals epsilon over 2, and then times the volume integral of E squared dt for all space. Okay, so this is the equation of calculating the volume, the continuous charge distribution when you assemble this continuous charge distribution, how much work you need to do. Now you have two set of equations to use. The first one is shown here, 2.43. The second one is 2.45. Okay, once you have those two equations, let's do an example here. Find the energy of a uniformly charged spherical shell of total charge Okay. Um, Now you have a sphere, and let's say you have some charges distributed on the surface. And what's the energy do you need to assemble those charges? First, let's use the equation 2.43. W equals to 1 over 2 sigma V times dA. It's pretty straightforward. And then the potential at the surface of the sphere, let's say, is calculated in this equation, which has been calculated in previous chapters. You can check 2.7, the equation or exercise 2.7, and then you can easily calculate this integral, and the final answer is here. This is the first way. The second way is, let's use this equation. If you want to calculate the energy, then work equals to this integral. Okay. So from this equation, let's say inside the sphere E equals to 0, outside E equals to 1 over 4 pi epsilon 0 Q over R squared. And the direction of E is radial direction. So this conclusion has been made in this chapter in the previous sections. So E squared equals to this term squared. And then the work you need to do is E squared, which is shown here, E squared dt. So it's this is E squared, and dt. What is dt? It in spherical coordinates, dt is shown here. So if you do a integral of this term, finally you get the answer, which is here, which is the same, of course, as the first way. If you forget why dt equals to this term, go back to the chapter 1 and see the spherical coordinates. In that section, we have introduced what is dt in the spherical coordinates, and dt can be described in this dr, d theta, d phi equation. Okay, so that's the way of calculating energies in two different situations. The first situation is a set of charges, and that's point charges. The second situation is for a continuous charge distribution. And we have given you some conclusions or some equations to do the calculations. So in the homework, most of the time, you just need to use those equations to do the calculation. Okay, so that's all for this chapter. For the chapter 2.5, it's conductors. We're not going to take it in our exams for the conductors. So please read this section by yourself. It won't be the exams. So when preparing the exams, our final exams, perhaps what you want to do is you want to just focus from 2.1 to 2.4. Okay, that's all for today. Thank you, guys.